Okay, so we're going to move into kind of like a new-ish topic with respect to what we're going to learn in this chapter. And again, it's still dealing overall with this idea behind energetics and stability of alkanes, okay? Coming away from this chapter, this material that we're going to learn here is probably going to be one of the more important things that you're going to learn. We're going to utilize Newman projections, which is what we're going to talk about quite a bit as we move through the remainder of the course. So it's important that you guys understand what we're dealing with here and how to actually visualize these alkanes and then be able to project or draw these Newman projections from them. Okay, so also things to note, we are going to be dealing with, again, with energetics, with stability. But a lot of what we're going to be dealing with can actually be aided with the help of a molecular model. So at the beginning of the semester, I told you, molecular models are helpful. I'll tell you when it's probably helpful to utilize them. This is that point in time, right? These Newman projections are kind of hard to see when we're dealing with stuff that's on paper. And so if you did have a molecular model, this would be the time to maybe start to utilize it. And I'll try to make a video of drawing Newman projections from models so that you can kind of help see how it would be useful. Okay, so what we're going to deal with here is the fact, number one, we're dealing with alkanes, right? So we've been talking about alkanes. And alkanes, again, are hydrocarbons that mainly the big takeaway is have only single bonds. Okay, so we only have sigma bonds with alkanes. We're only dealing with single bonds. Now, what we also find is that with sigma bonds are allowed free rotation about the bond axis, right? When we talked about the difference between sigma and pi, we talked about how, the sigma bond, you don't break that orbital overlap if you rotate that bond. Whereas with pi bonds, right, where we had that side-on orbital overlap, you do break it if you rotate it, so you can't rotate pi bonds, right? You can't rotate double or triple bonds. You can rotate single bonds, right? And so because we are allowed that free rotation, single bonds do rotate. And what we're going to talk about is kind of the ramifications about those rotations and the various different what we call conformations that our single bonds or our molecules can take on because those bonds are allowed to freely rotate, okay? Now, a couple issues with this, right? We have been drawing, at this point in time, our bond line structures, right? So when we draw our bond line structures, we know that carbon is represented by all of our little vertices and all of our little endpoints in our bond line structures. And again, when we're dealing with alkanes, the type of carbon that we're dealing with is sp3 hybridized carbon, right? So most important with respect to that, we're dealing with tetrahedral carbon, right? And so when we draw these bond line structures, what we're trying to imply is, again, these carbons are tetrahedral. Anything we draw in the plane of the paper or in the plane of the board is all supposed to be in the same plane, right? And so these two bonds are essentially implied to be in the exact same plane, meaning that the remainder of the atoms that are attached to that carbon, which again are going to be those implied hydrogens, are not in the same plane. So if you got a tetrahedron right now and you put two bonds in the exact same two-dimensional plane, you would have one thing that is coming out at you, right? And so the way we drew things that are coming out at us was via our wedge, right? So for this carbon right here, if we actually had a model of this guy, we would have a hydrogen that was coming out, pointing out at us, and we would also have another hydrogen that was pointing away from us, right? And so again, we're trying to replicate this tetrahedral structure. Anytime we draw a solid line, that solid line is saying that those guys are in the same plane. So if two of those bonds are in the same plane, then we would have one thing that's coming out at us, which is what we denote via our wedge, and we would have one thing going away from us into the board, which is what we denote via our dash, okay? Okay, so we're taking that, right? We're taking this idea behind bond line structures, and we're trying to assess the various conformations that can happen around these various bonds. Because again, we're going to be allowed free rotation. And so that's what we're moving into. That's kind of the entire purpose of this next section. Now, the way we draw it with respect to bond line structures is kind of hard to visualize, right? These various different rotations or these various different conformations, okay? And so because of that, we actually utilize a new way to draw things to help us visualize these different conformations that are available, right? So what we're going to do is we're going to take our wedge dash bond line structure, and one thing that we can do with it is we can draw what is called a sawhorse projection. And in a sawhorse projection, we've taken this bond line structure and we've rotated it 45 degrees, right? So we're taking this guy and we're essentially rotating it, and we're imagining what it would look like after that rotation. And that's what we get in our sawhorse structure. Again, this guy is our front carbon, is this guy, and this guy is what we're going to call our back carbon back here, okay? Now, these sawhorse projections are kind of difficult to draw still, right? So there's an easier way that we can draw this to imagine these conformations again. And so what we're going to do is we're going to take our sawhorse and we're going to again rotate it 45 degrees. So we're going to rotate again, and we're going to be left with what is called our Newman projection, okay? So just as a note, we're going to deal with a lot of different projections, right? And again, these projections are just different ways to visualize our original bond line wedge dash structure. We're just looking at different ways that make it a little bit easier to see what we're talking about comparatively to having to draw this over and over again, okay? So now I'm going to explain how we get this and what this means compared to coming from sawhorse or coming from wedge dash. Okay, so the way we imagine this is we will take our wedge dash projection, or I should maybe say bond line projection, or we'll take our sawhorse projection, and we will imagine that we're staring down a specific bond axis. So people always draw these kind of like, you know, imagine eyeballs just floating in the air. But what we're trying to do is imagine what it looks like if we're staring down this carbon-carbon bond axis. Where are the various things around this, okay? Now, the way we draw this is we're going to have two different things. We're going to have what we call our front carbon, all right? So this guy is our front carbon. And the way we represent our front carbon, what we're looking at, or the first carbon that we see as we're staring down this bond axis, is we represent it by this little dot right in the center, okay? So first step in drawing Newman projection, which is what we're trying to do. So Newman projection from a wedge dash or a sawhorse projection is drawing that front carbon. We're just going to illustrate that via a nice little dot, okay? So now, as we continue to look down here, what we're going to do is we're going to draw the bonds away from this front carbon by essentially trying to replicate where they're at, right? So as I look down this bond, this thing, in my vision, essentially looks like it's pointing straight down, right? So this bond is going to be represented coming from my front carbon, pointing straight down. And so that's a hydrogen. I'm going to represent it by whatever it's bound to. This thing, if I can get another color here, this guy, if I was looking at it, again, pointing in the direction of the eyeball, it would appear to me as if it was pointing up and to the right, right? This guy looks to me like it's pointing up and to the right from my front carbon, whereas this guy, this other guy, looks to me like it's pointing up and to the left. So I can also draw that guy over here, up and to the left in my Newman projection, okay? So again, this is this front carbon that we're imagining. We're now going to project and imagine us visualizing this through to this guy, which is what we call our back carbon. And the way that we represent our back carbon in Newman projections is we represent it via a big circle, right? So we have our front carbon represented by that dot. That back carbon is essentially something that we can't really see, but we represent it via a circle. All right, so again, as I'm looking down this bond axis, I'm now looking at the things that are attached to this back carbon. And as I'm looking at that, I see that this hydrogen looks like it's pointing directly up, right? So I'm going to go ahead and represent that by drawing a line that's pointing directly up from my back carbon. Then I have, let's say, this guy, again, that as I'm looking down at this, looks like it's pointing off and to the right. So down and to the right. And then I have this guy, as I look through this, that looks like it's pointing down and to the left. Okay, so this is how we're going to get these Newman projections from either sawhorse projections or our bond line structures. So now if I wanted to draw this in just all one color, again, I would have my front carbon represented by that dot. I have a bond down to hydrogen. I have a bond up to hydrogen. I have a bond up to hydrogen. I'm then going to draw my back carbon via a circle. I have a bond up to hydrogen. I have a bond down to hydrogen, and I have a bond down to hydrogen. Right? So this overall is this Newman projection for this molecule, which is just ethane, looking down this carbon-carbon bond axis. Okay, so it's important to get kind of practice doing this, right? And so I'm going to go through another example that's looking down a bond line structure of a little bit more complex of a molecule, okay? So right now, what they want us to do is they want us to take this bond line structure. So again, this is our bond line structure. And they want us to draw the Newman projection looking down the bond that they've illustrated via this arrow. So if you want to imagine there's an eyeball here, it's kind of creepy. It's looking directly down this bond axis, okay? So they want overall the Newman projection looking down this bond axis, okay? So again, my first step here is looking at the carbon that we're looking down. All right, so right now this guy is a 1, 2, 3, 4 carbon structure, right? Another way that they could say this, if we went ahead and numbered our carbons, we have 1, 2, 3, 4. They could say, oh, draw the Newman projection looking down the C2 to C3 bond axis. That's another way that they could state this, okay? So if I'm looking down this guy, right, I'm going to represent that again in my Newman projection via just a dot in the center, okay? Now, as I look down this guy, this thing, which is in the exact same plane as the bond I'm looking down, appears to be coming straight down. And as a note here, this is not a hydrogen, right? If we terminate in a carbon, then this is a CH3 group. Another way to state that is this is a methyl. Right, so we can represent that as we draw this Newman projection as just saying methyl, or you could also have said CH3 as well, right? So those are two exact same things. I'm going to go ahead and write CH3 just so that we make sure that we keep our carbons. So as I look down this, I'm looking down here, I've got a CH3 group. Now, they show us a wedge for the bromine, right? And so that wedge, as we look down this, is coming out at us as we look at it. But if I'm looking down this bond axis, to me, this is to my right and it's up. So I can draw that bromine to the right and up. There's another bond there that's being implied though, because they only show us 3 of them. So there is an implied hydrogen that's actually going into the board at this point in time. Because again, we've got 2 bonds in the same plane. The other bond has to be coming out at us. The other bond has to be going into the board. So that implied hydrogen is going into the board. And as I'm looking down this bond axis, that other hydrogen, it appears to be pointing up into the left. Right, so again, it's hard because like I can't, I'm using my hands to try to imply what I'm looking at, right? But you guys can't see that, so it's hard to necessarily do that. Okay, so again, this is our first step. This is our front carbon. So then the next step is drawing our back carbon. Again, how do we represent our back carbon, right? We represent it via circle, right? So we'll go ahead and draw a circle, right? Looking at this guy. Again, we're looking down this exact same bond axis, right? So if we're looking down this, then this thing appears to be popping up, right? And again, this thing is the exact same thing that we saw over here. This is a CH3 group. So coming from our back carbon, that methyl group is up top, popping directly up. We have this bromine. Let me try to use a highlighter here. We have this bromine that as we look down, coming this way, appears to be pointing down into the right. So we can draw that with our pen down into the right from that back carbon. And again, there is an implied hydrogen that now, as we look down this guy, is pointing down into the left. Okay, so this is the Newman projection for this molecule looking down the C2 to C3 bond axis, right? This was carbon 2, this is carbon 3, this is the bond we're looking down, and this is what we would see if we were actually pictured here. Maybe I should draw a human, you know, like a stick figure. So if we were actually here and we were looking down this bond directly, this is what we would see, or this is the visualization of what we would see. We'd see a methyl group on that front carbon pointing down, a bromine on that front carbon pointing up and to the right, a hydrogen pointing up and to the left. We would look through that, we'd see that methyl group pointing up, we'd see that bromine pointing down into the right, and that hydrogen pointing down into the left. Okay, so go ahead and try this one out. So I've drawn 3 different molecules, and I have shown you what bond axis I want you to look down, and I want you to draw the Newman projection looking down those bond axes, right? So here we're looking down this bond, this carbon-carbon bond. I want you to draw the Newman projection. Here we're looking down this bond. I want you to draw the Newman projection. And here we're looking down this bond. I would like the Newman projection from that. Okay, so get some practice with this, give this a try, maybe do the first one. So we'll start with this guy, see how you do, and then maybe pause it and move on to the next 2. Again, that I would go ahead and push pause, work on this, and then come back for the answers. Okay, so I'm going to start with this molecule to the left over here. We'll call this, I hate when I do that. We'll call this molecule A. Again, we have, let's say, 1, 2, 3, 4 carbons here. And so we're looking down. If we go 1, 2, 3, 4. For this bond, we want the Newman projection looking down the C2 to C3 bond axis. So again, if I do this, first thing I'm going to do is I'm going to start with my front carbon. We have our front carbon here, right? And again, we're going to represent that via just a nice little dot. So we don't draw the 3D perspective here, but we can imagine that this guy is on our wedge coming out at us, and then we can imagine that this guy is on our dash going into the board. So now I'm going to focus first on what this guy is down here, this bond that's pointing down. So again, this is a carbon. It is a methyl group, right? So it's a C3 group or CH3 group. Same thing here. We've got a carbon methyl group, and here we've got a carbon methyl group, all right? So if I drew this in my Newman projection, the thing that's coming down is this guy. So this guy's coming down, and I'll go ahead and say CH3. The thing that is pointing up and to the right is this guy, and I'll draw that as CH3. And then the thing that is pointing up and to the left is this guy, and I'll go ahead and draw that as a CH3. Okay, so that is my front carbon. We're now going to look down this at my back carbon. And for my back carbon, I only have one thing that's drawn that's attached to it, right? So we know that the other 2 things for that bond, because again, we're dealing with tetrahedral carbon, is a hydrogen. It has to be coming out at us. And then we also have a hydrogen that has to be going into the board. Those 2 things are implied. Okay, so now, as I look back down, if I was looking here through this bond, the only thing I would see is this guy sticking up, right? So I'm going to go ahead and draw my back carbon as a circle. I see this methyl group sticking up. So this guy is CH3. It's attached to my back carbon. And then the other 2 things I would see is a hydrogen here that's pointing down into the right. So I draw that as a hydrogen. And then I have a hydrogen here pointing down into the left. Right, so, oh, pardon me, this is a CH3. So this is the Newman projection looking down this bond axis. We've got our front carbon, and then we've got our back carbon, Okay, so hopefully you guys did well on that one. Go ahead and try what we'll call B here, and then come back for the answer. Okay, so Again, if we were numbering this, we'd have 1, 2, 3, 4, 5, 6. So this question, they want us to draw the Newman projection looking down the C3 to C4 bond axis. And again, maybe some of you are wondering, why did I start numbering 1 over here at this position as opposed to over here? And again, remember, when we number, we want to give the first substituent the lowest number possible. If I had started numbering over here, that would have given 1, 2, 3, 4. 3 is lower than 4, so we're going to start numbering over here. That's why I started numbering on the right instead of the left. Okay, so again, first thing first, we're going to draw our front carbon. Front carbon is carbon 3. We have this dash going into the board. That dash is again representing a CH3 group. We have bond here. We have bond here. These guys are in the same plane. And so just as a reminder, that means that there is an implied hydrogen that has to be coming out at us. Okay, that's important to know when we're actually trying to draw the Newman projection. Okay, so first things first, we have our front carbon. If I look down at this guy, then the first thing I see is this same thing, or this bond that's in the same plane as the bond we're looking down, that appears to be pointing down. The only thing to note here is that this thing is a CH2CH3 group. So there are a couple different ways that we can represent that. If it's a 2-carbon chain, like I've just said, we could say that that is an ethyl group, and we could represent it as ethyl or ET. We could also just give the molecular formula for it. So this is a CH2CH3 group. But again, it's everything that's coming down here, right? So it's this bond with everything attached to it. So I'll go ahead and write CH2CH3. And again, I could have said ethyl, I could have said ET to represent ethyl as well. Okay, so now I'm looking what's pointing up and to the right. So the thing that's pointing up and to the right is this guy, which is a hydrogen. So I'll go ahead and draw that on my Newman projection. This is a hydrogen. And then the thing that's pointing up and to the left is this guy. So I'll go ahead and write that on my Newman projection. This guy is a methyl group. Again, I could say CH3. I could also represent that as methyl. I could also represent that as Me. That's another way that we represent these guys. Okay, so that is all of my front carbon. Now I'm going to look down to my back carbon. The only thing I see drawn is this bond to these guys, right? So we have this bond here that's pointing up. Again, there has to be 4 bonds to carbon here, so we know that there's an implied hydrogen coming out at us, and there's an implied hydrogen going into the board. Let me draw that a little bit better. Make it visually more appealing. So this guy's coming out, this guy is going in. Now, as I look down my back carbon, I'll go ahead and draw it as my circle. The thing that I see pointing up is this guy, and again, this is a CH2CH3 group. So I'll go ahead and represent that CH2CH3. Now, as I look down this bond again, I see the hydrogen pointing, let me turn, I see the hydrogen looking down to the right, or looking down this bond, I see the hydrogen that's pointing down and to the right as this guy, right? So again, I try to situate myself so I can kind of visualize this. If anything is pointing into the board, coming from here, then that's going to be down and to the right for me. So this guy, this guy is this guy. And then here we have anything pointing down and to the left, it would be coming out. So this guy is this guy. So note that there's a separation here. This was a methyl group and this was an ethyl group. Again, another way to have drawn this would have been hydrogen, ethyl, methyl with a circle, and then ethyl, hydrogen, hydrogen. Okay, so then finally, we'll go with number C, or letter C, like how I just completed. erase all my conventions. I just forget them all. Okay, so for this guy, we've got carbon, 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 carbon. We're looking down the C2 to C3 bond axis. And we're wanting to draw the Newman projection from there, okay? So go ahead, give us a try, pause the video, and then come back for the answer. Okay, so again, we draw some weird eyeball. We're looking down this bond. We're going to draw our front carbon first. On our front carbon, we've got a bromine that's coming out at us. I don't know why I try to overdo that. Again, we've got another bond to a carbon up here. Again, this is a methyl group. And the thing that is implied is on the dash going into the board, this is a hydrogen. This is for our C2 carbon. For C3, we've got a dash with a chlorine that's going in. We've got a bond to another carbon that's in the same plane. And so then we know that there's an implied bond coming out at us, which is a hydrogen. Okay, so I'm going to draw my front carbon first. So we have our front carbon. As we look down this thing is pointing directly up. So this guy's pointing directly up. Again, this is a methyl. So we can represent that as not an E, a CH3 or an Me, or you could write out methyl. As we look down this, right, that bromine that's coming out at us, if I rotated my body to look down this, that bromine is pointing down and to the right. And that means that the hydrogen is also pointing down, but it's going into the board, which is to our left at this point in time. Okay, so that is front carbon. We'll do back carbon. So now as we look down this at our back carbon, the thing that's pointing down is again that CH3, that methyl group. So this is a CH3 group. Now as I come out, this thing that's coming out at us, if I turn my body, it's actually pointing up and to the right. So that hydrogen is pointing up and to the right. And then this chlorine, which is going into the board, again, as I rotate my body, is pointing up and to the left. So it's kind of ugly as I draw it like that. If I go ahead and redraw it using our little methyl ethyl convention, I've got a Me, I've got a Br, and I've got an H, and then I've also got an Me, I've got an H, and I've got a chlorine. So a couple different ways to draw the exact same projection. Okay, so give this a shot because it's difficult. Again, hopefully, if this is not making sense, I may make a video with some more spatial awareness to kind of get you guys in the mindset of how I look at this. But go ahead and give these guys a shot and then email me if you have questions with respect to that.